Okay. Happy Monday, you guys. We will be talking about the data path, essentially hardware that is going to support our MIPS ISA, right? So today our discussion will be focused on the hardware to support all the instructions. Well, I should change that. If I say all the instructions, then it becomes very overwhelming right away. So what we are going to do is talk about 8 instructions, a very small set of instructions, and then we'll see what hardware do we need to support that. So what is going to happen is, think about a puzzle, right? So if you're trying to put a puzzle together, first we talk about what pieces do you need and for what reason, and then you can start stitching them together, right? So that's what we are going to be doing today. We will be stitching components in the data path together to support MIPS ISA. You will be seeing things like a register file, you will be seeing muxes, you will be seeing ALU, adders, things like that. Everything that is in the data path. Before we get into the lecture itself, let me talk a little bit about the exam. So after white paper, sure. So exam 1 is 1 week from today, right? So it's Thursday. For that, June. No, not 1 week from today. It's 1 week from Thursday. Today is Thursday. All right, today is Thursday. I keep forgetting which one is Thursday, which one is Monday. All right, so where is it? 24th? Yes, 24th. Let's talk about time. When is it? It is going to be during class time. To online. So you're going to submit things on Gradescope. Next, lectures 1 through 9. So 9 is today. So whatever we cover up till today's lecture, data path included, that is going to be on the exam. So whatever we cover on Monday, not on the exam. Homeworks 1 to 3. 2 is due tonight. I will be posting 3, which is essentially your 32-bit and 64-bit conversions. Should not be that difficult for you guys to get through, but homework 1, 2, and 3 are going to be part of exam 1. Activities 1 through 8. The one today is the 8th activity, right? We gained 1 lecture, so that's why the lecture number is 9. Yes, 24th. So where are you guys going to be at? People online are going to be online. People in the room, you guys want to be in here, or do you guys want to be in your dorm room? Wherever you guys want to be. I'm flexible. Okay, here, it's an open book, open notes exam, right? So I'm going to give you guys the option of whether you want to be here or not. If everybody sort of is leaning towards, I'll take it at home, then I will not print exams and I will not bring them to class. But if majority of you say, oh yeah, I want to be here, I want to take the tests as they used to be, then I will print things, I'll get it over here so that you can, so you save your scanning time essentially. So can I see some hands? If who wants to take it in person here in this room? 3, 1, 2, 3, 4. Oh, you guys are not. All right, so about more than half the class actually wants to take it, right? Um, So how do we do this? All right. Okay, let me think about this a little bit because I want to be consistent in terms of um, how things go. Here, can I see some proper hands? How many of you would take it here in this room? Like proper hands? All right, way more than half the class. All right. So you guys can, is it fair to say about 10 or 12 people showed their hands? So what I'll do is I'll print exams and I'll get it to you for you over here. You can take it in the room, and I will be over here as well, monitoring how the other exam goes. So whoever wants to come in person to take the exam, come over here. And this applies even to the people online. If you are interested in coming to the room, to the actual room to take the exam, let me know. So maybe I can create a sign up sheet, give it to you guys for you guys to sign up. Okay, all the others, you're going to get the exam. You're going to write it on a piece of paper. You're going to answer on pieces of paper, scan them, upload to Gradescope. When is a good date for review? So I think Wednesday of next week is probably going to be too late, right? So maybe Tuesday of next week for a review. I'll talk about logistics. I'll talk about topics. I'll give you guys a few ideas. Tuesday of next week, I'll plan Tuesday afternoon. Right, Tuesday afternoon of next week, I'll plan a review session. Monday, again, classes, right? So Monday I have 2 classes, and there will be something or the other that day. Even the students have classes after 1:30 p.m. So Monday is probably not a good idea. I'll conduct the review session on Tuesday, record it, so that the people who are not there in the review session can watch it. And at that time, I'll talk more about the logistics. Okay. Other concerns, questions? Did I miss something? If I did, I will cover it in the review session. There's one resource that everybody needs. That. So if you are going to be in person over here, you don't need to bring it. I'll give it to you. But if you're going to be online, you will need this. Okay, let's continue with our lecture here, which is about Datapath. So what are the steps for designing Datapath? The first step is going to be to study our MIPS ISA or any ISA. Why do we need to study an ISA? Well, to support the Datapath, we are going to need to know size of the buses, size of the ALU operands, sign of the ALU result, size of the registers. How many registers do you have? So we are going to need to study the ISA, the instruction set architecture, in detail, right? So registers involved, instructions involved, the memory organization that is involved. We are going to study all of that because we are trying to build hardware to support that ISA. And we are going to put one real register for each register in the ISA. How many do we have? We have 32-bit registers, right? So we are going to have 32 real registers made out of what? D flip-flops, right? So we're going to have those 32 registers in our data path. And we are going to add a few more for internal use. We are going to have interconnections for each register transfer. So for example, if you want to transfer contents of instruction register into, contents of program counter, you read the program counter, then take the contents of memory and put it in the instruction register. That was your instruction fetch cycle. You're going to have register to register transfer operations. And that can be supported by interconnections, right? So we've got what? Buses, we've got ALU, we have got wires or interconnections, registers. So you're going to see a lot of hardware today. And the best way of going about understanding the data path and how it is assembled is to look at one thing and then build on top of that. In fact, there's a better way. Look at all the puzzle pieces and then start stitching them together, growing them, right? So stitch two together and then add third one, add fourth one, and so on. Select data path components, which is the next one. For example, what? Select what data path components. Do I need a mux? Do I need an ALU? Do I need a shifter? Do I need a sign extender? And I'm selecting the data path components to support my instruction set architecture, right? The ISA. So every time I look at an instruction, I'm going to try to answer this question. What component do I need to support this instruction? So, and I want you guys to do that as well. Whenever you see a branch instruction or a load instruction, try to think about what hardware do I need to execute this one. Once we select all the data path components, we'll try to assemble them, meeting all your requirements. There are two design principles that we are going to think about while we are making these choices. One is make the common case fast, which is something that we have heard from day one. Whenever you are trying to make the computer fast, your data path is going to have to be fast. Whatever common instructions you have, you're going to design hardware to make them fast. Second, simple and regular instructions allow for you to make a faster data path. What is the data path? Data path is all the hardware to support one instruction getting executed, which has 5 stages, right? Instruction fetch, decode, execute, blah, blah, blah. At the very end, you have the update program counter to the next instruction. So all of that has to be executed. And if the instruction set is simple and regular, you can do it in a faster manner. Now, what can happen is this. If I showed you the last slide of this lecture, it can be very sort of confusing, right? Oh my gosh, how am I going to look at this? How am I going to understand this? Let's just see. So that's the last slide of this lecture, right? So that's the end result. But we are going to not go directly into this, because if we do that, then we are sort of talking about a lot of details all at once, right? That's your single cycle data path. That's the answer to today's lecture. So we are going to talk about components, and then we'll try to stitch them together. That's the approach that we are taking. Hopefully, by the end, that seems trivial. We talked about this. Now, let's talk about simplified MIPS ISA. Why are you talking about simplified MIPS ISA? Because if I took the entire ISA and talked about the hardware required for that, then it can be even more overwhelming than the slide that you just saw. So I'm going to only consider 8 instructions. 8 instructions. And I have a mix. I have a mix of some branch instructions, some load word, store word, or memory reference instructions, some arithmetic instructions, and then I'll include jump instruction later on. So I have a little bit of a simplified MIPS ISA, 8 instructions, but a mix. So in terms of memory reference instructions, I have load word and store word. Right? Load word and store word are the only 2 instructions in which you are actually reading or writing to the memory. Right? Load word, you're bringing something from the memory to a register. Store word, you're taking the contents of one of your 32-bit registers to the memory, the other way, right? Next, arithmetic logical instructions, add, subtract, or, and set on less than. These are your arithmetic or logical operations that we'll try to include in our simplified ISA, simplified MIPS ISA. And then one control flow instruction, which is your branch when equal. Compare the contents of 2 registers, and if they're equal, branch. If they're not equal, just do PC plus 4. And we'll include jump later. Now, let's count these. How many instructions do you have here? 8 so far, right? So if you wanted to tell the ALU is where your instructions are actually getting executed. So if you wanted to tell the ALU to perform one instruction versus the other, how many bits are you going to need? 3 bits, right? So you're going to need 3 bits, 3 bits for ALU control, right? So with using these 3 bits, I can tell the ALU to add or set less than or whatever instruction. So you'll see this later on. Okay, next. The first step of each instruction is going to be to update, not update, right? The first instruction is what? Fetch, right? Fetch the next instruction is your first step. Then you read the registers, execute the operation, update the program counter, go back, right? Fetch the instruction, read the registers. Why? Because sometimes you will have 2 registers, sometimes you will have 3 registers. So for example, if I take add instruction has 3 registers, but I don't read all 3 of them. How many do I read? I read 2 of them, right? I read 2 registers, which are my source registers, add the contents of the 2 registers, and then put the result back in my 3rd register, right? But read registers is sort of operand fetch, right? So this is instruction fetch. Then somewhere over here, there is decode instruction. And we are not showing that because it is the control unit, the finite state machine that is taking care of that. We are talking about the data path right now. Then we read in registers, which is your operand fetch. Then this is your execute. And then this is your, what is that, housekeeping. PC equals PC plus 4 for us. Right, so those are your 5 steps. We are not including the decode instruction right now. That is for each instruction. So this again and again and again. It's going to keep repeating these basic steps. These are some of the things that we have already talked about. We spent a lot of time talking about these things. We'll just do a quick review of our MIPS ISA. All instructions are 32 bits long. All programs are word aligned. Instructions are word aligned. Data is byte addressable, but instructions and programs are word aligned. There are 3 types of instructions: register, R type, immediate type, and your jump type. They have their own specific format. R type instructions have opcode, RSRT as your source registers, destination register. Some instructions support shifting, and then you have your function code. Function code to identify variations of the same instruction, like add and then add u. Right? Next, I type, you have got your operand, 2 source registers, immediate offset, add I, or I, load word, store word, also fall in that same category. Branch, equal, branch, not equal. All of those are I type instructions. The last one is your jump instruction, which is opcode followed by your 26-bit target address. So this is your jump and link. Those are the 2 instructions that are J type. So op, that's your operation. Which operation do you want to do? RSRT and RD, those are your 2 source registers and 1 destination register. Where should they be? Right? Operation is no hardware, right? Operation is not a hardware. Operation is knowing what hardware do I need to support an instruction. But registers, those are real, right? So I've got 2 source registers and 1 destination register here. What am I going to need to support that? You will need 3 registers. Where are those 3 registers? In the register file, right? So the register file is going to be a block which has 32 registers. And right now, for say R type instruction, I need to be talking about 3 different registers in those 32. Then I have the shift amount. Like I said, if you wanted to do shifting for a specific R type instruction, you can do that. We have seen an example of like shift left, shift logical left for that. Function, variation of opcode. This immediate field, which is your 16-bit field in the ITAP instruction, can be used for immediate constant or can be used as the address. What type of address? Let's see. Whenever you're talking about memory, you need a target address. Target address is computed by adding two things. One is the base address, and then there is an offset. Base address is in the register. Offset address is going in your instruction, right? So this immediate offset can be two things depending on the instruction, immediate constant or an offset address. Last one, JTAP instruction is simply a target address, 26-bit. You have to shift left by 2 to get 28 bits, essentially multiplying it by 4, and then get the 4 most significant bits from the current program counter. That will make your 32 bits. We won't worry about the JTAP instruction today. We will try to support R and ITAP instructions generally with the hardware today. Next. Now, this slide is particularly important because I'm going to try to ask you guys with every instruction, what do you need for this? What do you need for this? What do you need for this? In terms of hardware, what hardware do you need for this? So instruction fetch, which is common for all instructions, that is straight. That's not a very interesting thing, right? So you have PC. PC contains the address of the next instruction. So try to look in the memory for that address, contents of PC. You're going to find the next instruction over there and then load it into the instruction register. So that's going to be your memory read. And I'm going to distinguish. I'm going to distinguish memory reads for instructions and for data. Right? Instruction, so I'll call it instruction memory and memory, everything else. So instruction memory is part of my memory that only has instructions. Right? So I'm reading instruction memory to find out what is the next instruction, next instruction, next instruction. But in terms of load word, store word, all the other memory references, that is a separate memory. In reality, they are the same, but I'm going to be referring to them as two separate blocks. Next, in terms of instruction execution, say you take add instruction. What do you need to support add instruction in terms of hardware? So add instruction is take two registers in your register file, add the contents, put it back in one of the registers in the same register file. And when you're finished with that instruction, do some housekeeping, which is to do PC equals PC plus 4. So what hardware do you think you will need to do these things? Good. An adder and an adder, right? So what I'll do is I will say this guy right here, I'm going to call that an adder. I need an adder to do this. And it's a constant, PC equals PC plus 4, add 4 all the time. And see this, I can use it to do this. And I can use it to do this. And I can use it to do this. I can use it to, these are not exclusive ORs. These are me pointing, oh boy. So I can use the same adder to do all of these things, right? Yes, and here as well. So whenever you need to do PC equals PC plus 4, and it looks like I need to do that for every instruction, I will use an adder which has two inputs, PC, current PC, and 4, right? And I'm going to just leave that adder as is. I'm not going to use it for anything else. Now, what am I going to use for this? See, sometimes I need to add, sometimes I need to subtract, sometimes I need to OR. So what kind of component in the data path should I use for that? ALU, right? So an ALU would be better suited for this. Now this ALU is going to be 32-bit, right? Because the inputs are 32 bits, right? And then the output is 32 bits. So that's a 32-bit ALU. So you've got an ALU in there, you've got an adder in there already. So we have got hardware to support this, we have got hardware to support this. Next, move on. Or immediate is take the contents of one of your source registers, bitwise OR it with 0 extended immediate. Whatever you had in the immediate constant field, the last 16 bits, extend it, 0 extend it to 32 bits, so that now you can do a bitwise OR between two registers, RS and all of that, right? So ALU used to do that. Now, what is the ALU getting as the input? Well, you see, register, 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 not a register. So what does that mean? The ALU inputs should be selected depending on what type of instruction is being executed. So what am I selecting over here? Sometimes I'm selecting, oh, by the way, RS is same, right? This guy is the same. So one end of the ALU input is sort of always there, the RS field. The other is either RT or output of a 0 extender, output of a sign extender. Later on, you see RS plus sign extender. So sometimes it's the output of 0 extender, sometimes it's the output of sign extender. So what I'm going to do is this. I'm going to need some hardware to select what goes to the input of the ALU. What hardware will support that? Was it? A mux, right? There it is, a mux. I can use a mux and I can call that ALU input mux, right? And that mux can be used to select whether the operand, second operand of the ALU is RT or this guy or this guy. I can select that. I need a mux for doing that, right? So I'll just write that. I need a mux. All right, next. There is a 0 extension over there for OR immediate. Next, when you go to load instruction, over here, load is to do what? Load is take contents of memory, load them into a register. Now, when you're loading, you are talking about two things, a base address and an offset address. The base address is a register, in a register. So 32-bit register, so fine, that's there. But the offset, that's part of the instruction, right? The offset address that goes in the load is part of the instruction. That's your 16-bit immediate. But if it is not, now the question is this, I need to take this guy. What is there in this? Can anybody help me find out what is there in this? Base address. So base address goes in the register, and I can actually do this as well, right? This guy is also base address. So the base address is going in RS, but the offset address needs to be sign extended. Question, why couldn't we use 0 extended? So here I had 0 extension. Here I have sign extension. Well, a few questions. One, why? What are they? How are they different? But I think you guys are ready to answer. Evan, you can go ahead. Why 0 extension for this guy? Why sign extension for this guy? There you go. Nice. So whenever you're doing this sign extension, that's an offset. The offset is relative to the base address, which means that base address, you can go above it, you can go below it, right? So positive, negative. So you need sign extension to preserve its sign. Zero extension is essentially padding it up with zeros in the front, because otherwise, if you padded it with ones and you did OR, the result would be ones, right? You are overwriting on that. So that's why you do an OR, zero extension for OR, but you do a sign extension for load word or store word. So let's if you are new to this idea, let's talk about this. I like to do a simple exercise here where I have zero extension here, and I have sign extension. Sign extension here. I will consider 4 bits. Say I have B0, B1, B2, and B3. And I have these same guys again for sign extension. I am considering 4 bits. If I wanted to zero extend it to 8 bits, what should I do? I want to zero extend it to 8 bits. What should I do here for zero extension? 4 zeros up front, right? Let me just quickly make a note here. Over there, BI belongs to the set of 0, 1, where I equals 0, 1, 2, or 3, right? So that's my bit. Okay, so over there, I'm padding it with zeros so that the next number I have, and I'm ORing them, these guys don't make a difference to that. If they were ones, they would have made the OR result 1 for those. Now I can do the bitwise OR. In this case, 8. In our case, 32. Next, sign extension. What should I do here? 4 to 8 bits. 4 B3s. Right, so over here I'm doing B3, 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 B3. Sign extensions. Now, B3 can be 0 or can be 1. Right? So when B3 is 0, what does that imply? So when I be doing that sign extension, we are doing that sign extension either here, or we are actually doing it here as well. But we are doing that for load word and store word. For load word and store word, we are computing the target address. Target address equals base address plus offset. If B3 is 0, what is the relationship between target address and base address? Above it. Or equal? Yes, target address is greater than or equal to base address. And then, of course, I can talk about the other case. B3 is 1, then target address will be less than 1. Jump up or jump down? You guys see that? Yeah. Let's come back. Okay, so let's go into this again. So we need a zero extender. Some component, some hardware that can take a 16-bit number and extend it to 32 bits. Yeah? Zero extender. Sign extender, same thing. A component that can take in 16 bits and extend it to 32 bits using sign extension. PC equals PC plus 4, we already know we need to do an adder there. Next, for store instruction, this addition happens the same way. Sign extender, need that. ALU, need that. Add them and then read the memory. Read the memory and put it in the, sorry, not read the memory. Put the contents of RT in that memory. So that is going to be memory read and write instructions. Next, we have a branch when equal. Now, what am I going to need to support this branch when equal instruction? I need to check this condition, RS equals RT or not. What hardware do I need to do that? Right? Comparator. Okay, so Franklin says comparator, and he's right. Comparator. But comparator is expensive. Good. Okay, so that's a simplified comparator, right? But that's still comparing. What's that? Just subtract, right? So if you subtract the contents of two registers, if the answer is 0, they're equal. If the answer is not 0, they're not equal. Subtraction easier, simpler than comparator. So instead of comparator, we can start using a subtractor. Subtraction. And look at 0 result, right? So an ALU has the result, and there is also an additional flag, which is output of an ALU, which is 0. So you can just monitor that flag. If your subtraction, if you're now you are looking at it as a subtraction instruction in which you're monitoring the 0 output. If the 0 output is active, a 1, then you know that those registers were equal. Now, so that's what we use to do this comparison. Now, how about this? PC equals PC plus 4 plus sign extension of this. We already had this sign extender, right? We can use the same sign extender for this, right? But this guy had immediate constant, but for this guy it is immediate constant multiplied by 4. Why? Because this is a branch instruction. For branch instruction, your offset is in words, right? Do you guys remember that? Because there is no point branching in the middle of a 32-bit sequence. You branch to the start of a 32-bit sequence, start of the word. So for that, you have the sign extender, the same hardware that was used earlier. How do I multiply by 4? Shift left 2, right? So here, I needed a sign extender. Now I need a shift left 2. Shift left 2 to do this, right? By multiply by 4. Now, next question. Sometimes my program counter is being updated by the next instruction, PC plus 4. And sometimes my program counter is being updated by PC plus 4 plus sign extension of these things, right? How do I choose? What hardware do I need to choose? Was that? Go ahead, confident. A mux, there you go. So I'm going to need mux to find out what is the source of my PC. PC source. Either it can be PC plus 4, the output of that adder, or it can be PC plus 4 plus the sign extender, output of the sign extender. Do you see that? So I need a mux to do that. All right, questions here. Now we have essentially talked about puzzle, pieces of the puzzle. What pieces of the puzzle do we need? We have talked about that. Let's talk about the instruction fetch unit. Why do we need to talk about this? Well, that's the first thing that we do, instruction fetch. So we need to talk about that. So you see, hardware, right? We are going to be talking about what hardware do we need to support each step of your instruction cycle. First one is instruction fetch unit, which is step 1 involves fetching the next instruction. So instruction register should be updated with the contents of memory. Location is in the program counter. So program counter has an address. You look at that address in memory. Whatever is there, that's your instruction register. That's your instruction. Next, after you do this, what do you do? Update the program counter. Updating the program counter can either be sequential or you can have branches and jumps, right? One after the other, sequential, or you can be branching things. So PC equals PC plus 4, that's one option. Or PC equals something else. What is that something else? Something else could be PC plus 4 plus output of the sign extender, right? Or in case of jump, PC could be target address directly, right? So something else, or PC equals PC plus 4. We need to choose how to update the program counter. So what do you have here? You have your program counter, which is a register. So it's a clocked. It's a D flip-flops constructed with D flip-flops. Those are clocked. Now what is going to happen? This program counter is going to provide you with the address of the next instruction. So where do you go looking? You go looking in the instruction memory, right? Because you have now the address of the next instruction. You look in the instruction memory, you read that instruction. That's going to be your instruction word, right? You guys see that? So this is memory. You read the memory, and we are calling it instruction memory. And whatever is that is at that address, that's your instruction. But that's your PC, right? But how are you going to find out next? Well, you take the current contents of PC, go into this next address logic. It could be add by 4, or it could be add by 4 plus the output of the sign extender. So what will this have? This will have adders, this will have multiplexers to choose between those two options. And then you update the program counter by that. You guys see that? So fetching the next instruction requires instruction memory to be read, a program counter, and also hardware that comprises of adders by 4. You will need multiplexers. That's it. Right? I'm not going to include the sign extender. Why? Because the sign extender and the shifter, right? You're going to also need to do shift by 4 sometimes. Right? Shift by 4. Sometimes you need to do the shift by 4. Sometimes you need to do the sign extension. I'm not going to put it over there. I could, but I'm not going to put it there to compute the next address. I'm just going to say address, adders, and then the multiplexer. Next. Let's take a look at some of your components. Again, we are looking at, we are zoning in on the puzzle pieces, right? I found one here, I found one here, I found one here. First, ALU. 2 inputs, 1 output. ALU A side, ALU B side, output 32-bit result. Another result for 0, can that be used for? For comparison, right? Why is this ALU control 3 bits? Well, we have looked at a simplified MIPS ISA with 8 instructions, and we already said three bits are going to need, we are going to need 3 bits to figure out which instruction to execute. So 3 bits for ALU control. That's your ALU. This is sort of a very, very important component in our data path. This is where instructions get executed. Next, adder. Why are we going to need this adder? We need to do that PC plus 4 business, right? We are going to need adders. So you have a 32-bit register here, 32-bit register here, go through an adder, carry in sum and carry out. Sum is your 32-bit output, carry in 1 bit, carry out 1 bit. Next, muxes. Now with muxes, you are selecting between options. Sometimes they might be simple muxes like a 2:1 mux or a 4:1 mux. But you could also have something like this, where you are selecting between 2 registers, right? A and B. A is 32 bits, B is 32 bits, and depending on this select line, you're selecting one or the other. When are you going to have this situation? One or the other. So you see, if you look at the R-type instruction versus I-type instruction, in R-type instruction, you have 3 registers, RS, RT, RD. In I-type, you only have RS and RT. So you are going to need to select, you have input of bunch of registers, you are going to select one of them to go through. So you will need that mux, this sort of mux to support that. This, what are you going to call this mux? If we had to name this, we would name this what? 2:1 mux, right? 2:1 mux, but it's a 32-bit one. So we are going to call this a 32-bit 2:1 mux. We are going to see a lot bigger muxes in today's lecture. Now, next, shift by n. Why do we need shift by n? Multiply things by 4. Why is the input 32 bits and the output 32 bits? Go ahead. Right. So when you were doing this, right? So if I go back, that shift by n module is used to do this, right? You had already done the sign extension. So the sign extension output was already 32 bits. You just need to move it left. That's what multiplies it by 4. But when you look at the sign extender, input is 16, output is 32, right? So 16 goes in, 32 comes out. For the zero extender, again, 16 goes in, 32 comes out. We know why we need zero extension, to support the RI instruction or AND I instruction. We need the zero extender. We understand why we need the sign extender. Load word, store word, computing the target address. Shifter, multiply things by 4. Adder, PC equals PC plus 4. Muxes, you will have choice. Which PC to update, for example. You will need mux for that, right? So you guys are, I hope you guys are now seeing that each of these components has a specific purpose to support our instructions, right? Questions so far? How are we doing? Going slow, going fast? Is okay? Next, data path storage components. Sometimes you will need buffers, sometimes you will need memory, and sometimes we'll have register file. Why do we need buffers? Well, buffers function as this, temporary storage for bits. Now, when we start talking about pipelining, we are going to have a lot of buffers to support pipelining. Those are going to be called interstage pipeline buffers. But we'll put that in our data path later on, not yet. We'll put that in there after exam 1. But this is that buffer. What is it? It's a placeholder for bits. You need to write data into that buffer, and whenever you want to find out what is in there, you need to read data from that buffer. Write enable is a control input to that buffer for you to enable write. When it is disabled, you are reading. But it is also clocked. Why? Because it's constructed out of flip-flops. And all flip-flops we know are clocked. So this clock is going to essentially dictate when are you writing things to it, or when are you reading things from it, and so on. So buffers, we need that. Next, memory. What can you do with memory? Two things. I can write to it, I can read from it. So if you want to write to it, what do you need to do? You need to enable write. You need to provide an address so that you know where to write in the memory. And whatever you want to write in that memory goes in data in. Data in, 32-bit. Address variable, right? We are talking about a 32-bit address, but that data could have a different memory organization. Write enable is just 1 bit. Also clocked. One memory access clocked after the other. Now, when you want to read it, what do you need to do? What do you need to do when you want to read memory? Disable write, provide the address of where you want to read, and once you read that, the contents of memory will go into a memory buffer register or memory data register, which will be available on this data out 32 bits. Yeah. Remember, memory has address and data, right? And address goes in the memory address register, buffer, memory buffer register. Next, register file. This is important. So I want you guys to be asking these questions. Read register 1, read register 2. Why do we have read on register 1 and 2? Well, like why 2 registers are being read? Why is 1 register being written? Right? So you see, read data 1, read data 2. You are reading 2 registers. You are able to write to 1 register. All of this is what? Your register file. What does a register file have? 32 registers, right? So there are 32 registers in here. For example, if you say you have add instruction, If you want to execute an add instruction, pick out one register from there, read it. Pick out another register from the register file, read it. Add those two using the ALU, and then put the result back. So you see what is going to happen. Register 1. I will let you know which register I'm talking about by providing you the 5-bit code. Because there are 32 of them, I will need 5 bits to identify which of the 32, right? So register 1, register 2. Whatever they have is going to be read here and here. Where will they go to support the add instruction? They will go to an ALU, right? They will go to ALU after this. They will get added. Once they get added, they will go back. Once they go back to write data, right? Because I want to write, the answer goes in the third register, right? RD. So I will let you know which register it is going to, the third register, write register. I will provide the data over here, and I will also activate register write so that you can write it. You guys see that? So pick the source register, pick the second source register, read their contents, right, over here. Do whatever math you want to do, arithmetic or logic operation you want to do with those. Then you circle around. Sometimes you may want to just store it to memory. Then you will not circle around. But here, to support add, you're circling around and going back into your register file for the writing of the, or updating your destination register. Register write, that is a control for the register file, which will be active when you want to write to a register. For what type of instructions will register write be 0? Here, multiple choice, multiple answer, right? Question is, what type of instructions register write is going to be 0? R, I, J. Good. J? J, okay, what about I? Do I need to sometimes write, will I need to write to a register file in I type instructions? No, that is it, right? So add I, right? That is an instruction in which you will add a number, a constant, to a register and put the result back into the register. So you will need to write the register there, right? So for jump instructions, you don't. For I instructions, add I, you do, right? Can you guys think of an instruction, an I type instruction in which register write is 0? Go ahead. A branch instruction. A branch instruction, you don't need to do a register write. So depending on the instruction, your register write control will change. So it's not associated with R, I, and J. It's actually associated with the instructions. Let's see. But once you know the instruction and you know how it should function, you can find that out, right? You can reverse engineer what register write should be. Go ahead. So store word, what is going to happen? Store word is from the register to the memory, right? Then I'm not writing to the registers. So 0. Yep. But load word, I have to write. The difference is this: when you're doing add, the source of that writing to the register file is coming from the ALU output. When you're doing load, the source is coming from the memory. So we will have another mux, or another mux, 2:1 mux, which will be used to select the contents that are going in here. Are they coming from ALU or are they coming from memory? So we'll have another mux at the very end of our See, whatever you read can be written back, right? Whatever you read from the memory is being written back, load, or whatever arithmetic you just did is going into that. You guys see that? So that's sort of memory to register, that is supporting that. Let's come back to, and the thing that we just talked about is your register write. Let's go back to where were we? Right here. Okay, so let's move on here, no questions. So you've got a 32-bit data, all right? Let me just write these. What is the size of this guy? 32 bits? 32 bits. That is just one. How about here? 32, right? 32-bit registers in there. Right? All the 32 bits registers in there. And there are other hardware components also. We'll talk about that. Because you see, depending on these 5 bits, you are going to need to provide these 32 bits, right? So this 5 bits will tell you which register you're going to have to use a mux to select that register so that that contents can be go over there. Right? So you're going to have a lot of other hardware, essentially muxes and decoders in the register file to support those selections. We talked about that next. So a register file, and we are talking about a read, right? So here is your 32-bit register, right? So register 0, 1, 2, 3, and so on up to 31. All your 32-bit registers are part of the register file. All of them, the contents of all of those guys are going into 2 muxes. So let's talk about the size of these muxes. What is the size of this guy? Was that 32:1, right? So it's a 32:1 mux. But how many bit are all the input? There you go. So 32 bit, 32:1 mux, right? So there are 32 inputs. Each input is 32 bits, right? So I have this read A register. So these are what, 5 bits? Can I say this is 5 bits? Those 5 bits are essentially selecting. These 5 bits are selecting one out of these 32 inputs to go through. I see that. So that's 5. This is 32. Each of these is 32. There's a dot, dot, dot in the middle. So don't forget about that. In the past, some people have been confused about this being 5 and that being 5. This is not 5. This is 32. Don't forget these dots. Next. So that's how I select the contents or read the contents of one register file, one register. Next, I do the same thing for the second one, right? So all of those 32-bit registers are going into the second mux. There is another 5-bit sequence I'm going to tell you to identify my second source register so that you can read that data over here. So the size of this mux is also going to be a 32-bit, 32:1 mux. We can read 2 registers at the same time. Now, can both the registers be the same? Yeah, absolutely. They have independent muxes, right? So I can have the same 5-bit sequence here and here, right? So if I have the same 5-bit sequence here and here, I will be reading the same register. So I can do something like add S1, 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 right? So I can do that. I'm reading S1, I'm reading S1, adding them, putting the result back in S1. Right, go ahead. Reading in parallel, yes, absolutely. Oh, that you bring up a good point. Here, I wanted to talk about that over here. You see, in this, I wanted an ALU here to execute these guys, and I wanted an adder over here. Why couldn't I use just the ALU even to do this? Right? But perfect. Can I also add one more reason to this? The other reason being, I'm doing addition over here. I'm using executing the code here, right? This is housekeeping, and this is execution of an instruction stage. There are two different stages. If I try to use the same hardware for the two stages, then I will not be able to do things in parallel, right? I'm sort of creating a bottleneck in terms of speed over there, right? So I'm going to use this adder to do the housekeeping step. I'm going to use the ALU for the execution stage. Yeah. Next. Now, how do you write? There is a conceptual register file write. So you have computed the answer of your, say, add instruction. You want to write the result of that add instruction back into the register file. How are you going to do? You're going to need a few things. One, the write input has to be a 1, right? You should be writing. What is that write? I should actually say register write, right? Reg write, like that was the control that we were referring it to as register write. So that has to be a 1 for you to write. The other is you need to identify which one out of the 32 registers you are writing to, and then you also have to give the data that you are writing, the 32-bit data that you want to write to the register. Now, this register number, 5 bits, right, is actually going into a N-to-1 decoder, so that the outputs for 5, how many outputs do I get? All of your 32, right? So all of these 32 outputs, one of them is going to be active, depending on the 5-bit input. That is actually going into AND gate, right? All of them are getting register write. All of them are getting individual outputs out of that 5-bit decoding output. So tell me what is going to happen if, in order for the output of one of these AND gates to be a 1, what needs to happen? Go ahead. Right. So this has to be a 1. Can I say that? Right. So if any output has to be a 1, the first condition is register write has to be a 1. Next, this guy has to be corresponding to that. So for example, if this is, say, 30, right? So this has to be 30, right? So that means in 35 bits. What are they? You convert that into 5-bit sequence, you will get 5-bit sequence. 32 minus 1. No, 31, right? So 31 is what? All ones. That is your 30, right? So if you give this guy 1, 1, 1, 1, 0, and this is 1, then your last but 1 AND gate will give you a high. Everything else will be a 0, right? A 0 here, 0 here, 0 here. Everybody else will be a 0. That is what? That is activating, you're controlling each of your registers. So for a register, when you want to update the contents of a register, what do you need? You need the data to be written, and you also need a clock or an active edge, right? So that's those inputs. The C input is activating it. This register can be written now, provide the 32-bit data. The 32-bit data is actually hardwired to all of them. One of them is going to actually work. And then that's how you update one of your registers of the register file. We can write one register at any time on clock edge when that becomes active. Next, can this register that we are writing to be the same as the one that was being read? So we have three, right? RS, RT, RD. Can RD be the same as, we already said RS and RT can be the same. But can RD be the same as one of those RS, RT? Yes. Why? Because you see, we are reading things and we are writing things. So there could be an issue, right? In terms of time, are we doing things correctly or not? So will it work? Can I have them to be the same? And if it does work, why is it able to work? Good. One after the other, yes. So you're reading first, go to the ALU, execute the instruction, then your results come back, right, and get written. So they are in time, they are spaced out. So you are able to do that. It's not happening at the same clock cycle. It's happening at different clock cycles. You have that ALU execution stage in the middle to separate them out. Okay, other questions? Were there questions? No? Okay. Now let's talk about the data path for R-type instructions. We'll try to include those three registers in there. So for an R-type instruction, that is the format of your instruction. 6 bits opcode, RS, RT, RD. Two of them are source registers. One of them is a destination register. Then you have your shift amount and function. So how is RS, RT, and RD going to go into your register file? You see, RS goes over here. That functions as the read register 1. RT goes over here. Read register 2. RD, write register. 5 bits, 5 bits, 5 bits to identify the two source registers being read and the destination register being written. Now, what do I have to be careful about? Over here, there are some things that are not written explicitly. For example, this is 32 bits, right? You guys see, this is, say, if this is 31, then this is 0, right? That's a 32-bit sequence. 20, 30, 29, and so on. Yeah? Some part is going here, some is here, some is here. Which one is RS? Which bits of the instruction register are going for RS? So RS is here to here. Wait. 25 to 21. Agrees? Everybody? Yeah? All right, next. RS, RT. Instruction register. What to what? 20 to 16. Next, RD. Huh? You guys see that? So those are not shown over here, but sort of when you go all the way to the last diagram, you will start seeing that. Instruction 25 to 21, 20 to 16, 15 to 11, so on. Right? So now you know what those are. Those are corresponding to RS, RT, and RD fields. Let's go back. So for the R-type instruction, all we need to worry about is arithmetic or logical operations, right? So where do they happen? They happen at the ALU. Read data 1, which one? RS. Read data 2, which one? RT. perform the ALU operation, add, subtract, or whatever you have. How are you going to know? The 3-bit ALU operation code. The ALU result being written back to the register file. So you see, this is only for data path for R type, right? We are not looking at, oh yeah, we actually used a mux at the end to select between memory or ALU. We are not talking about that just yet. Questions here? Here is an interesting question. How big is the instruction? What is the size of the instruction itself? Actually, 32 bits, right? These five are going here, right? Where is this going? The opcode is actually going to a control unit. The data path is separate from the control unit. The control unit is going to be looking at your opcode, right? It is not going to. Now, next, function. These function bits are actually going to control the register file, memory to register, the controls of your muxes, right? So when we start looking at the next lecture or the lecture after that, which is going to be basically on the control unit, ALU control, then we'll talk about what are the hardware components we are going to need to look at the opcode field and then send out the corresponding control signals for all the muxes. Register write, memory to register, and there will be many to select the source of the muxes, for example. All right, data path for load and store. So for load and store instruction, the goal is what? Compute target address. Take the base address, take the offset, do the sign extension for the offset, add them to the base address, and then read the memory. When you read the memory, you put that result back into a register. That's for load. So load is sort of doing this, right? Load is this arrow. Whatever you have in the memory, address. Which address? Base address in RS, offset address computed by sign extending the offset, right? Once you add those two, you read the memory. When you read the memory, you can load into an RT. So this arrow is supporting load. Yeah? And this arrow is supporting store. Register to memory or memory to register. Store, load. Now, there's a difference here between the data path for R-type. In R-type instruction, we needed 2 source registers and 1 destination. Over here, we don't have all of them. We simply have 2 registers. You see, one of them to identify RS, one of them to identify RT. Right? There's no destination register. RD field is not there. Right? So, in some cases, RT, whatever register you have in this, will function as a read register, and in some cases, RT will function as a write register. So tell me, for store, RT is functioning as write register or read register? For store to memory, right? So read, you're right. And for load, you are loading things from memory into a register, right? So you're writing now. You guys see that? the same register field RT, which is sort of this guy, right? This is base address. Okay, so that's sort of going here, and that is being used for base address. But RT, right, that depending on load or store, it can either function as the read register 2 or the write register. Can you see that? Okay, so now let's compare. What is the difference between this? Just look at these three, RS, RT, RD, and this. RS, RT, RT. 3 registers, RS, RT, RD. 3 registers, RS, RT, RT again. Which means to differentiate between R-type and I-type data path, I need a MUX. I need a MUX to select which register I'm writing to, right? Sometimes that's my RD field, and sometimes it is my RT field. You guys see that? So that brings me to this piece. I have register destination, RT field selection essentially. It could either come from this or it could come from this. It is going to be coming from this RT to, so this is the one that I'm choosing, right? This is the one that is different. Sometimes it is RD, this is your RD. And this is your RT, right? Sometimes it is RT and sometimes it is RD. Now, quick question. What is the value of register destination for add? You want to execute add instruction. What is the value of register destination? A 1. Wonderful. You see this? 0, this goes through. 1, this goes through. You want RD to go through, right? So for add, it will be a 1. How about for load? For load, this is 0, right? RS, RT, this also has to be RT. So for load, it would have been a 0. You guys see that? All right. So now we know why this MUX is being used. Let's see. I'm going to erase this so that there's no confusion there. Come back to this. Okay. Let's talk about the other things that we need to support load and store. Register file, read RS or RT. Sometimes RT might be making sense. Sometimes it will not. When will RT make sense? Read data of RT. When you're doing store, then you will read this register because you will want that to be written to memory, right? So for store instruction, this will make sense. When you're doing load, it may be present, but it will not make sense because we will not be writing to memory in that case, right? So even if the data is there, we are not going to be doing anything with it. So when you read data 1, you read data 2, you've got RS over here. Why? Base address. RT over here. Why? Because that's your storage for storing. Now we need what? Add base with offset. RS needs to be added using ALU with sign extended 32 immediate. So the immediate is also coming from the instruction. So let me answer, talk about this. Immediate 16 is what? Instruction what to what? Zero to 15? Yeah? Take that part of the instruction, sign extended to 32 bits, add it to the RS, because RS has base address. Base plus offset, what did you get? Target address. That target address is the address you want to access the memory whenever you want to either write or read. Now, sometimes you want to write or read because we have what? Load and store. When you want to write, use memwrite. When you want to read, use memread. Right? These are active high signals. Memread for reading, memwrite for writing. Now, when you read, what happens? When you are reading, what happens? You know the address, you are reading, whatever you read will appear over here on read data. Will support what? Will support load instruction, load word. Yeah. Next, you want to write. Make this a 1. Provide the data to be written over here. Provide the address of where you want to write over here. Then data will be written to support store word. Good. You can. So it doesn't happen, but if there are some special cases when you talk about pipelining, those are identifiers of some special cases happening. So we have 2 of them. Memread, memwrite, register write, ALU operation. All right, so we have talked about these things. Other questions? All right, conditional branch. This is what? Branch when equal or branch when not equal. 6 bits for opcode, RS, RT, followed by 16-bit immediate. In this case, what is it? This is your offset, right? Offset relative to PC. Format of the instruction, branch when equal, RS, RT, 16 bits. Those 16 bits are used again to compute your target PC, right? PC plus 4 plus sign extended, 16 bits converted to 32 bits, multiplied by 4, to shift left by 2, to multiply it by 4, and then you add it. All of that is sort of expressed over here. So what do? Instruction fetch, as usual. Next, you compare the contents of RS and RT, calculate the branch condition. How are we doing that? We are reading RS, read data 1 from the register file. RT, read data 2 from the register file. Go to the ALU, subtract. The 0 result is what we are monitoring, right? And if the condition is satisfied, if they're equal, if the 0 result of the ALU is active, then PC gets updated by PC plus 4 plus sign extended of the immediate, right? First the sign extension happens, then you multiply it by 4. And then you add to that. Why are we multiplying by 4? Because the branch offset is in words. You convert it into bytes. That's how you compute your offset. Else, you just go to the next instruction, which is PC equals PC plus 4. So these statements, these things that are happening in the branch instruction, we are going to see how the hardware plays out for this. So register file, still there. ALU, yeah, absolutely. ALU 0 is what we are going to try to monitor to find out if the branch condition is met or not. We have read data 1. RS goes here, right? RS goes here. RT goes here. What do they have? That is read here and here. Goes to the ALU, subtraction operation, 0 result. That is going to the branch logic. Essentially, that will dictate whether we jump to PC plus 4 or we jump to PC plus 4 plus that sign extended output, right? So mux is there. So it's going to a mux essentially. But we also need to compute PC plus 4 plus sign extended, right? So this is going to give us our 16-bit immediate, make it into a 32-bit sign extended offset. That is going to be in words, shift left by 2 to convert it into bytes, and add it to PC plus 4, right? So that will give you the branch target address. Now, if this is 0, if the ALU result is inactive, then don't branch to that target address. Branch to just this, PC plus 4. If this guy is active, then update PC with the branch target. Questions? Putting it all together. Now, my hope is that once you see all the pieces together, it's going to be a lot more sense. It's going to make a lot more sense than it did at the very beginning when I just showed you guys the picture. Now, so putting it all together, we are going to consolidate all the 3 diagrams for art, I, and the branch instructions. We will try to handle all these 8 instructions, the simplified MIPS ISA. We're going to target a single data path, single cycle data path, 5 stages, 1 full instruction getting executed. It can do all of the above in 1 cycle. Each part is used once per instruction. We are not duplicating things in 1 instruction. Some parts may be replicated and some parts could be shared by using muxes. We have essentially talked about these ideas earlier. Combine R-type and load store. For R-type instruction, we needed the register file, then we needed the ALU for our arithmetic or logical operations. For load and store, we added the memory, right? So what we are stitching together over here is register file, ALU, and the memory. Now, our ALU source, you see this? The ALU source. One ALU source is from the register file. That is always going to be there. But the second ALU source could either be read data 2, which is one of the register in the register file, or it could be this 32-bit sign extended. Can you think of an instruction in which I may have to choose this guy as the ALU source? What type of instruction? Not type, just give me an instruction. Which instruction I may have to do this? Branch instruction. All right, branch instruction. What else? Was it? Load word, store word, all of those instructions are being used here, right? Offset address, make it into 32 bits. That's your ALU source. Now, think about a few instructions in which you are using this path. This should be simpler. Right. Add, subtract, or whatever. Right. So that's your mux to select between this or that. Next, the memory to register. We talked about this a little bit. Sometimes, not sometimes, whenever you are writing to the register file, right, those contents could either be coming from the memory or those contents could be coming from the output of the ALU. For add, it is coming from the ALU, right? For load word, it is coming from the memory. So I have another mux here, and I have a control, memory to register. 0, one of them goes through, one of them goes through. So the top input and the bottom input are not necessarily 0 and 1. You have to be a little bit more careful than just that. You have to sort of look at, so here you see this, 1 is top here, 0 is bottom here. So don't assume one or the other. It will change. Can you guys think of why they are changing? Sometimes there's a 0 here, there's a 1 there, and sometimes there's a 1 there, 0 here. Why do you think they are changing? Go ahead. I wouldn't say that. Wait, it's a simpler reason than that. No, just imagine what would happen if you switched this around. What would happen? Your diagram will look confusing. The wires will be running in weird manner. That's why you are sort of arranging it such a way that you are able to have a little bit more structure in the diagram. That's it. All right, let's see. Okay, questions about this. How did we stitch the R-type and the load store instruction together? Yeah, but sorry, things are going good. All right, let's continue here. Now we are adding the instruction fetch circuit. What is that? PC equals PC plus 4. We are adding that. Zoom out, zoom in on the left part of your diagram. Why? Because left part is going to be your first part, right? We are moving things from left to right. We have got our instruction memory. You give me the address, I will tell you what is that instruction at that address. What is the read address going to be? That is going to be your program counter. Program counter will keep getting updated by PC plus 4. So PC, add 4 to it, write it back to PC at the end of the instruction, right? And then that becomes your read address, read the instruction memory, and you get your next instruction to work on. Now, sometimes it can be PC plus 4. Some other times it can be PC plus 4 plus the branch target, right? So you're going to need to add another mux for the PC source. Generally, this is going to be the case, PC plus 4. Everything else is as is, right? Register file, sign extender, mux to select, ALU, memory, a mux to control which thing are you writing to the register file, memory or the ALU result. So all of those things are sort of similar to things over here. Okay, let's add the branch address calculation. So branch address calculation is what? After I do the sign extender, I will need to do the shift left by 2 to multiply it by 4. Then I will need to add it with PC plus 4. Right? So PC plus 4 is coming from here. We had added this earlier. PC plus 4 comes in, gets added to the, after you multiply by 4 and having done the sign extension, that's your branch target. So PC source is another control to a mux where you are either selecting PC plus 4, no branching, or you are selecting PC plus 4 plus branch target. Right. So you see this? PC can get updated using two things, this or this, depending on what PC source is. Again, PC source comes from decoding of your opcode bits. PC plus 4, sequential. PC plus 4 plus branch target for branching. Again, in the next lecture, we'll add jump to this as well. Everything else is as is, just the highlighted part in yellow. That's what we have added on, the branch address calculation. Questions here? How we have added the branch address calculations? No, straightforward? Okay. That's your full single cycle data path to support these 8 instructions. Instruction memory, PC, PC plus 4, PC plus 4 plus, to select between PC plus 4 and the branch address, PC source, ALU, memory. We have talked about this register here, the mux here, the controls, memory read and memory write. We've talked about all the things here. So the activity that you have today has two parts. One is the IEEE conversions, the standard 754 standards. That should be a breeze. Like that, you guys should run through that very easily. The other part is based on this exercise. Essentially, you're going to try to trace out what is the value of memory read or memory write or register write, memory to register. All of these, what should they be to support a particular type of instruction? One note, an important note that I would like to make is there are many block diagrams like this. There are many sources. Stick to one source. This is the one that is in your book. And I want you guys to use this particular source. They're all consistent, right? It's not that they are conflicting. They're all consistent, but they are, sometimes the one is at the top, 0 is at the bottom. Sometimes they're switched. So there are a few differences here and there. But try to stick to one. For the activity, use this. This is from your textbook, slide 21. Questions here. All the controls are being highlighted in blue in this case. So that is sort of decoding your operation, right? So when the control unit looks at the opcode bits, it will determine all these controls, all the MUX controls. Questions? For the 32-bit and the 64-bit double precision, single precision format numbers, if you guys want to use the online calculator to check, that is fine. But try to show work on the piece of paper that you're working on. For checking, for validating, an online calculator is fine. I'm going to be here for you guys if you guys have questions. If not, I will see you guys on Monday. Yes, Monday.